Quite often during our discussions throughout this course, we're going to be talking about graphing, and you may recall that graphing is accomplished on a plane that is called a rectangular coordinate system, or perhaps the Cartesian plane. It's called the Cartesian plane in honor of the great French mathematician René Descartes. You may also recall that the Cartesian plane is composed of two intersecting number lines, a horizontal number line called the x-axis and a vertical number line called the y-axis. The two number lines intersect at 0 on both number lines. And for along the x-axis, positive values lie to the right, negative values to the left. On the y-axis, the positive values lie above and the negative values below the intersection point. The intersection point is called the origin of the coordinate plane. Now, positions on this coordinate plane are identified using two numbers. Those two numbers are said to be ordered, and an ordered pair might look like this. The position 4, -2. It's called an ordered pair because the first item represents a horizontal distance, the second item a vertical distance, hence the order idea. These are called the coordinates of a certain point, and this is the x-coordinate and that the y-coordinate. Now, to locate a point, we begin at the origin and we move according to the distances indicated. 4 horizontally means from the origin go a distance of 1, 2, 3, 4, and then -2 means down 2 vertically, so we go down 2, and here then is the point for -2. Let's locate a couple of other points. How about the point -5, -3? From here, -5, that means to the left, is the negative direction horizontally, so it's -1, 2, 3, 4, 5, and then down 1, 2, 3. So here's the point -5, -3. Now I am plotting points or graphing according to the coordinates that we are talking about here. Suppose we are talking about the coordinates 0, 4. Well, let's see. 0, 4. That means the first component, the horizontal component, is 0. That means we don't go any distance this way. And then 4 means we go up 4 to arrive at the point 0, 4. And one more, the point -2, 0. -2 means to the left 2. You see the horizontal distance, -2 means to the left 2. And then 0 means no distance up and down. This is the point -2, 0. Okay, so we're graphing now. Now, if we have a place on the coordinate plane like, let's say this place, and we want to discover its coordinates, then we would count from the origin a horizontal and vertical distance to that point. So from the origin, 1, 2, 3, 4, 5, 6, 7 horizontally, and then 1, 2 vertically. So this is the point 7, 2. These are then the coordinates of that point. One thing we can do with our coordinate plane is we can actually develop a formula for calculating the distance between any two points. And this formula then would be called the distance formula. I can just give it to you here, but you might remember it a little better if we show how this formula is developed. I won't take a great deal of time with this, but here's the gist of the idea. Suppose we're talking about the point 2, 3 and the point 10, 9. All right, so these are the coordinates of those 2 points, and we want the distance between the 2 points. The idea is this. I'd like to calculate this distance, and the way that the distance formula is developed, it actually comes from the Pythagorean relationship, which is a relationship between the sides of right triangles. And if we drop a vertical segment down here and then a horizontal segment across to that one, then we have a right triangle formed. And in this right triangle configuration, if we call this side A and this side B and this side C, then we know that by the Pythagorean relationship, C squared is equal to A squared plus B squared. So we have C squared is A squared plus B squared. Now we're going to develop a distance formula, this distance along between the 2 points. So this distance C is what we're after here. So I want to solve this for C. Taking the square root on both sides, I find C to be the square root of A squared plus B squared. Now let's talk about the distances A and B. Now this distance A is a horizontal distance. The coordinates of this point, 10, 3. Now, horizontal distance along a number line, you may recall from before, is calculated as the absolute value of the difference in values, the real number values along the horizontal number line. Now here, we're talking about horizontal distances, so the components for horizontal distance are the 2 and the 10. So this distance A is the absolute value of 2 minus 10, or 10 minus 2, whichever. But at any rate, that A distance is this 2 minus 10, and it's being squared here. In a similar way, the distance from this point to this point, these are vertical distances now, so the second component comes into play here in these coordinates. So it's the absolute value of 3 minus 9 for that distance. So the absolute value of 3 minus 9, or 9 minus 3 if you'd like, and that value is squared. Now, absolute value was put into this distance idea when we were talking about distance on the number line because we wanted to make sure that the value was always positive. Well, it doesn't really matter in this context whether the value is positive or negative because we're squaring. And whether we square a positive number or a negative number, we get a positive result. So the absolute value symbols are unnecessary here, so let's take them off. We come to this situation. Now I'm calling this the distance formula, so we'll label the C value D. We'll just change the labeling on it, D for distance, you see, between any 2 points. So this is the general idea. Now here's what I want you to notice. You see the 2 and the 10 here, the 3 and the 9 here? Now those are actually, those came from this configuration of the right triangle. But the 2 here and the 10 here, gee, I used this 10 and that 2, but I didn't need to use this 10, I could use that 10. You see, I can just use the horizontal components of the 2 given points. And in a similar way, I use the 3 here and the 9. Well, instead of using this 3, I could have used that one. See, I have 2 vertical components here given in those 2 original points. So I don't really need this, the coordinates of this point in order to use this distance idea. I can just use the 2 points given. Now, to generalize the situation, whether I was using the points 2, 3, 10, 9, or simply x, y, or x1, y1, x2, y2. You see, I could use general points to make this kind of development or to develop this distance formula. And the distance formula then emerges like this. This is just a difference in x components, or a distance in horizontal distances. And this is just a difference in y components, or a difference in vertical distances. Now, the subscripted numbers here, the subscript numbers, just indicate that these are different x components. And these just say that these are different y components, and that's all. And because this is a 2 and that's a 2, this xy pair, they're related to one another. And the ones indicate that those rascals are related to one another as well. But that's really all there is to it. Now, to make the calculation, we would presumably go from the distance formula, plug the information into a step that looks like this, and perform the indicated operations to find that distance to be, I think in this case, it turns out to be 10. Well, one way that the distance formula can be used is to determine whether or not we have a right triangle if we're given the coordinates of several points. That is, given that we have the points 2, 1, 4, 0, and 5, 7, are these the vertices of a right triangle? Gee, if they are the vertices of a right triangle, then this relationship between the sides exists. You see, the Pythagorean theorem works both ways. That is, the way we generally think about the Pythagorean theorem is that if we have a right triangle, then we have a certain relationship between the sides. C squared equals A squared plus B squared. Okay. It's also the case, though, the other way around, that if we have any ordinary everyday household triangle and we have a special relationship between the sides, namely A squared plus B squared equals C squared, if we have that relationship, then we can determine that we have a right triangle. So it works both ways. Now, in order to determine whether or not we have a right triangle, what we need to do is calculate the distances between these points, you see, and then determine whether or not we have that special relationship between those distances. And those distances represent the sides of some triangle. It might be a right triangle, and we'll find out. Now, we'll use the distance formula 3 times. We want the distance between that point and this one, the distance between this point and that one, the distance between this point and that one. and then we'll check out to see if we have this special relationship. I want to make sure, though, we understand what we're doing. Let me just sketch what's going on here. We've got the point 2,1 about right here, the point 4,0, that's about right here. I didn't think about this a great deal before I started this. All right, here's 4,0. And then the point 5,7. Here's 5, and then up 7, somewhere up in this neighborhood, let's say. Now, are these points the vertices of a right triangle? It almost looks like that may be a right angle. I sketched it roughly, so it might be. You know, we just don't know. But that's the idea, that we want distance between the points in order to determine whether or not we have this special relationship between the sides of a right triangle. So we come out to the side, and we say, we're using that formula, and we say, I want the distance between, let's see, 2,1 and 4,0. So it's that distance then is the square root of, now I'm using that formula. Generally I say write the formula down, replace within the formula in the first step, and then make your calculations. Well, I'm replacing within the formula right here because I have it written down over there. Difference in x components would be 2 minus 4. It's squared, and I'm adding the difference in y components. That's 1 minus 0 squared. Now let's see, what do I have? I've got d equals the square root of, now let me simplify in my head a little bit. This is negative 2, squared is 4, so that's 4. This is 1 squared is 1, 4 and 1, 5. This is the square root of 5. Okay, good. Now, for another one, for the distance between, let's say 2,1 and that other point 5,7, I go, distance is square root of difference in x components. I've got 2 minus 5 squared plus difference in y's, that's 1 minus 7 squared. And then that distance is, this is negative 3 squared, that's 9. Negative 6 squared, that's 36. 36 and 9, that's 45. So the square root of 45. Okay, I have one more. I'm just backtracking over here. So I want the distance between the 4,0 and 5,7. So I have the square root of, let's see, difference in x components, that's 4 minus 5 squared plus 0 minus 7 squared. That's square root of, this is negative 1 squared, that's 1. This is negative 7 squared, that's 49. So this then would be the square root of 50. Now my three distances are, let's see, I might name these a little bit differently. I have them all labeled as D. That's kind of inappropriate because they're not all the same. So I might call this D1 and D2 and D3. So I've got, let me summarize here. D1 was square root of 5, D2 is the square root of 45, and D3 is the square root of 50. Now, is it the case that C squared is A squared plus B squared? Well, gee, what's A and B? Well, A and B are the legs of a supposed right triangle, and C is the hypotenuse. C is the longest side. What would be the longest one of these? Oh, it would be this. So is it the case that the square root of 50 squared equals the sum of the squares of the other two sides? That's the square root of 5 squared plus the square root of 45 squared. So this would be 50 equals 5 plus 45. Oh, sure, 50 is indeed equal to 50, and therefore we do have a right triangle. If we know the coordinates of 2 points on the coordinate plane, we know that we can use the distance formula to calculate the distance between the 2 points. Well, there's also a formula for finding the midpoint between those 2 points, and it's rather intuitive. That is the method of of calculation is rather intuitive. It works like this. Suppose we have a couple of points on the coordinate plane. We'd like to find the coordinates of the point that's right in the middle between those two. The midpoint formula conceptually works like this. It's just the average horizontal distance. You see, the average of the horizontal distances associated with the coordinates of those points and the average vertical distance for the y component of that midpoint. So it's average horizontal distance, average vertical distance. And averages, you know, are calculated by taking some number of things and adding them and then divide by the number of items that you have added. Now here we're just averaging a couple of horizontal distances and a couple of vertical distances. So we're adding two x values and we're dividing by 2 to get the average. And then you add a couple of y values and divide by 2 to get the average. And that's really all there is to it. So it's add the x components, divide by 2, add the y components, divide by 2, and these are the coordinates then of the midpoint. For the points that we have here, the x components are -3 and 7. Collecting those and dividing by 2, we get 2 for the x coordinate of the midpoint. The y components are 1 and 5. Adding those and dividing by 2, we get 3 for the y coordinate of the midpoint. The midpoint then has coordinates 2, 3. Let's see, 2 and up 3. Aha! Here's the midpoint of this segment.